All right, and for problem 3, we have a pipe flow problem with oil, and we're given the properties, density and viscosity, and we're also given the geometry of the pipeline, so 28 centimeters diameter, 330 meters length, and the average velocity of flow is 0.5 meters per second. Now, if we ignore any entrance effects, let's determine the pumping power required to overcome any pressure losses. So the first thing we have to do is figure out whether we have laminar or turbulent flow, and we're going to do that with the Reynolds number. So if we look at the Reynolds number, we pretty much have everything needed to calculate it. We have the density, we have the velocity, we have the diameter, we have the viscosity. So by plugging in 894, and then the velocity of 0.5, and the diameter of 0.828 meters or 28 centimeters, divided by 233. So that will give us a Reynolds number of 5372, which is less than 2300, which means that we have laminar flow. For calculating the pumping power, we need to first calculate the losses. So the head loss can be calculated directly using the friction factor formula, which we can use again. Hold on, let me write this. Which we can be used both for laminar and turbulent flow. And we only are missing the friction factor to calculate this. But we know that for laminar flow, that is equal to 64 over Reynolds. The rest of these terms we already know. So we've got 64 divided by 5372, the length, which is 330 meters, and we've got the diameter 0.28, we've got the velocity 0.5 square, and then we've got the gravity acceleration here. So that will give us head loss of 17.886 meters. Now, having the head losses, we can calculate the pumping power requirement, and that would be rho G H F Q. Now Q is equal to VA, or V pi d square over 4. So the power requirement would be equal to 894, 981, 17,886, and I'm just going to continue on the other line. We got 0.5, and then pi 0.28 square over 4, and that will give us power requirement of 4,829.4 watts, or 4.83 kilowatts.